So resistance is defined as the opposition to flow of a current in a conductor. Well, it's the same idea as thinking about a flow of a current in a stream. What would oppose the flow? Maybe if there was a bunch of beavers that built a dam at the end of the little stream, well, that would oppose the flow. That dam would be a resistor in a sense. And there are several things that affect resistance, and we're going to talk about those in a little bit. The second definition we have to make is called voltage, and voltage is really defined as a potential difference. And this happens when a positive charge flows through a circuit, and each coulomb of charge gains some amount of potential energy as it flows through the circuit in joules, and we're looking really at the ratio of energy gain per coulomb. Okay, remembering that a voltage source or a battery has two nodes, a positive and a negative node, thus creating the potential difference between them, enabling the positive flow to actually go through the circuit. Ohm's law tells us that the voltage is equal to the current times the resistance, and this is across any individual element in a circuit. So if you wanted to figure out what the resistance was of a certain material, say a light bulb, how much does it slow down the flow of the current, you could simply determine the voltage drop across the light bulb, and you could do that experimentally using like a voltmeter. You could figure out what the current is that you're providing for it, and you can figure out as a result what the resistance is. So traditionally, this formula can be thought of as resistance is really equal to the ratio of the voltage drop across that element to the current flowing through that element. Now, just so we're clear about units, voltage is measured in volts, current is measured in amps, but resistance is measured in ohms. And this is the symbol, okay, for omega. So if you had this symbol here, this is the symbol representing your resistance. Here's your amps, and here's your volts. Now remember, if we take a look here, we'll notice that we're talking about resistance really, and a lot of elements have a constant internal resistance. So say a light bulb had a resistance of 20 ohms, and you had a certain current going through it, you could figure out the voltage. But let's say we had some constant value here, right? So it's an object that doesn't change resistance. And what you'll notice is that if you double the current supplied, it will double the voltage across that resistor. If you triple the current, it will triple the voltage. Because these two things, again, you can see here, they are directly related looking at it this way. Or we could say that in order for this to be the same number, say this number is 5. Say the resistance is 5 ohms. The only way to get 5 ohms in the denominator, if we have, like, say we have, 7 down here, well, this has to be 35. But if that 7 doubles, if that 7 became, say the current became 14, well, then this has to be 70, because 70 over 14 is 5. So traditionally, we're looking at things that have constant resistances, and we'll see that again. The definition of resistance we can think of as the ratio of voltage to current. Now, Ohm's law, it's not really a fundamental nature of law, okay, but it only works for certain materials. And materials that Ohm's law holds true for are called to be ohmic materials, and they have a constant R value, meaning the slope of the graph below here we can see is constant. And we'll notice this because we're plotting the current versus the voltage, or the potential difference. Well, this is your I, right? This is your voltage here. So if we recall the formula we had from the last slide, resistance is really equal to voltage over the current. Well, we're going to see here that this graph is simply plotting the inverse of that, right? It's plotting the current versus the voltage as opposed to the voltage over the current. So what you'll notice is that the slope here, instead of the slope becoming R, the slope is just 1 over R, because these are the inverses, right? These are flipped around. This is taking the current over the voltage, whereas we had the voltage over the current. So, but still, if R is a constant value, then 1 over R is also a constant value. If this is a number like 5 ohms, then the slope of this line would be 1/5, right? 1 over R. But the idea that the slope is constant, it's a linear function, tells us that it is ohmic. If something were non-ohmic, meaning that the resistance is not a constant, we'll notice in the graph here that there's a curve to the graph. Okay, as the potential difference increases, the current increases, but not necessarily linearly, not in a linear fashion like it did before. So this curve here tells us that it is non-ohmic, just saying that the function here is not linear, right? Not linear. And the reason we can tell that, remember, here was our original formula, V equals IR. Well, this is thought of as, in this graph at least, R is thought of as almost like your slope, okay? If R is constant, the slope should be constant. This is like your dependent, and this is your independent. The graphs here, these examples, happen to switch those two. They plot current versus potential difference. Now let's take a look at 4 factors that affect resistance. And first of all, remember that resistance is really collision or result of more collisions between electrons and the metallic atoms in the copper wire, whatever the wire is made of. So the first thing we'll notice is that length is directly related. Shorter length, less resistance. Longer length, more resistance. And this makes sense. Think about a longer strand of wire. It simply means that there's going to be more chance for this electron to bounce around. When we think about drift velocity, whenever we think about that, the electron really is not sitting still, but it's kind of bouncing around, pinballing back and forth in here until it gets to the other end as it moves. The second thing we'll notice is that cross-sectional area is inversely related. Again, higher cross-sectional area, lower resistance. Smaller cross-sectional area, more resistance. And let's think about this for a moment. Well, here it's clear because, look, this is like a pipe when water's flowing through a pipe. Water can flow through this pipe a lot easier than water flowing through this pipe, especially if there's an abundance of water. Here, if you had a lot of water, it might get backed up. It's like having 4 pipe drains coming into one in your house. You'd want the big pipe drain running out to the ground and all the other pipes to be smaller so that when they come together, they could actually flow out. Whereas if you had 10 pipes that are an inch or 2 each, and then you had an exit pipe that was only a 1-inch diameter, it's going to get all backed up. All your water's going to get backed up in your sink and your shower, and it's not going to actually flow out. So a larger pipe means less resistance. So think about with water, okay, water flowing through a pipe. So same thing with the current here. Less resistance in the current, more resistance in the current. The third thing we're going to look at is the material, and we're going to look at different materials in general, but just to make it easy for us, we're giving 2 examples here. We're looking at copper and we're looking at iron. And copper has less resistance than iron does. And there are several materials, actually there's only one that I know of that's a natural material that has less resistance than copper, and that is silver. But because silver is so expensive, you wouldn't be using silver for wiring, you would end up using copper. The fourth thing to look at is temperature, and we'll see here that there's a low temperature, and up here there's a higher temperature. So we'll see that this is directly related also. As temperature goes from this, whatever this value is, to a larger value over here, we get greater resistance. So low temperature, low resistance, high temperature, high resistance, directly related. Example 1 says that the resistance of an air conditioner is 21 ohms. What is the current in the air conditioner when it is connected across a potential difference of 115 volts? So here's like your battery source. We're going to see that later on in our circuit unit. And this is the overall resistance of the air conditioner. And obviously the air conditioner is made up of many components, each with their own individual resistances, but we're looking at the overall net resistance of an air conditioning unit. So here we have a voltage of 115 volts. We've got a resistance of 21 ohms, and we're trying to find the current through this air conditioner or across the air conditioner. How many coulombs per second are flowing through this air conditioner. So we've got Ohm's law telling us V equals IR. We're solving for I, so I is equal to V over R. The current is equal to the voltage over the resistance. So we take 115 volts over 21 ohms, giving us a current of approximately 5.5 amps. Remembering, please, that amps are really coulombs per second. So what this really means is that we've got 5.5 coulombs per second passing a given point in the air conditioner. So 5.5 coulombs of charge pass a certain location every single second. And you can think of this in terms of electrons. You could say, well, how many electrons is that really? Well, if we know that there's 1.6 times 10 to the negative 19 coulombs in every electron, right? That's how many coulombs of charge, and this would be a negative charge for coulombs. Well, we could go ahead and take this number and divide it by this number here, and that'll give us the amount of electrons that are passing that given location every single second. Next, let's talk about a potentiometer. And a potentiometer is related to this topic because it's a special type of resistor. And the way it works is it has a sliding contact that changes the actual resistance in it. So for example, you walk in a room, you can turn the light switch on or off. Sure, you're opening or closing the circuit. But a light dimmer adjusts the amount of flow by changing the resistance with a metal sliding contact. A volume control, changing the decibel level, or a joystick on a game controller. Okay, a joystick on a video game controller would have altering signals sent to it. So if you push to the right more, the character in the game might turn right very quick as opposed to turning to the right lightly, and they might be panning to the right very slowly. Finally, the last thing we want to look at are superconductors and their resistance. And we mentioned this earlier already in another topic, but let's specifically talk about it now. And a superconductor, again, exhibits zero resistance below a critical temperature. So for example, this graph is showing us that there is constant resistance as the temperature increases, it increases at a constant rate. Right? Temperature goes, here's the temperature. Temperature goes up, the resistance goes up. But below a certain point, it drops dramatically. And then we have something called a critical temperature. At every temperature below this, in this case it'd be 4.15 kelvins. Okay, every temperature below this, the material exhibits zero resistance or negligible resistance. And what would happen here theoretically would be if you applied a sudden voltage to a circuit, it would continue forever and ever. If that wire were cooled enough, nothing would ever stop that current from flowing around. It'd be like a frictionless surface. That's what this really is. There's very, very little resistance or little friction stopping it.